morning, dear student. In today's lecture, we will discuss our fourth course of our syllabus, that is CHI-334, which is a practical course in which uh, there is a two section, that is some practicals are included in section first and some are included in section second. So we are very much interested in the practicals from the section first. So in section first, if you see the syllabus, different types of practical is there, some ore alloy analysis is there, and then some pharmaceutical, okay, that is determination of magnesium from milk of magnesia, determination of iron from tablets, pharmaceutical practical also is there, and some in organometallic preparation is there. Okay, organometallic preparation is there. That is, we are very much familiar with the ferrocene and the reaction, that is Friedel-Crafts acylation reaction. So in our practical course CHI-334 section first, there is a one preparation and its characterization, that is preparation of acetylferrocene and its characterization, that is it is an organometallic compound. So we are very much familiar with this ferrocene. So we know that this ferrocene, it is a sandwich compound. It is a sandwich compound in which the metal atom is Fe and the two cyclopentadiene rings are attached to this Fe, in which the Fe is in +2 oxidation state. Then if you consider this ferrocene, it is an 18 electron complex, and this cyclopentadienyl ligand, it is aromatic in nature, and therefore it will shows electrophilic substitution reaction similar to benzene. So it will shows electrophilic substitution reactions such as Friedel-Crafts acylation, Friedel-Crafts alkylation. So in theory we already discussed these points. So in today's lecture we are very much interested in the preparation, that is preparation and characterization of acetylferrocene. So we will discuss the mechanism, so which route is used for the preparation of acetylferrocene, and the characterization of the product which is obtained. So we consider the two possible routes are used in chemistry for preparation of acetylferrocene. The first one is in presence of acyl chloride and Lewis acid. So this reactant gives disubstituted acetylferrocene, and therefore it is not very useful. So the other method in which only mono acetylferrocene is obtained, monosubstituted product mono acetylferrocene is obtained, that is the reaction of ferrocene with acetic anhydride in presence of acids such as phosphoric acid. So we will discuss this route, that is preparation of acetylferrocene with the help of acetic anhydride and phosphoric acid. So the aim of the experiment, that is the aim of the experiment is that synthesis and characterization, synthesis and characterization of synthesis and characterization of acetylferrocene, synthesis and characterization of acetylferrocene. So if you consider a reaction, that is, we know this is your ferrocene. So we are very much familiar with this ferrocene in presence of acetic anhydride, that is CH3 C double bond O O C double bond O CH3, acetic anhydride in presence of 85% H3PO4, 85% H3PO4, and we get a monosubstituted acetylferrocene. So this is the reaction, this is our experiment. that is synthesis and characterization of acetylferrocene. So after synthesis, we will characterize the compound which is formed with the help of H1NMR spectroscopy. So the reactant molecule shows only in reactant molecule all protons are equivalent. So what is the change when the product is formed, that is acetylferrocene is formed. So this is our experiment, that is synthesis and characterization of acetylferrocene. So let us discuss first the mechanism of this reaction. So let us discuss the mechanism of this reaction, that is mechanism of acetylferrocene formation with the help of acetic anhydride and the phosphoric acid. So the first step in the mechanism, let us see the mechanism. Let us see the mechanism. The first step is the protonation. The first step is the protonation. Protonation of acetic anhydride of acetic anhydride with phosphoric acid H3PO4. So protonation of acetic anhydride with phosphoric acid. So this is your anhydride. Okay, this oxygen having two lone pairs, each oxygen having lone pair, and this is your phosphoric acid, that is P double bond O. This is your OH, this is your OH, and this is your OH. So this lone pair of oxygen, it will takes this proton, and what do you get here? So here what do you get? Double bond O, O, double bond OH, having lone pair having a positive charge, and this is your CH3 group, and what you get here, that is O minus P double bond O, OH, OH. So the phosphoric acid after protonation, it will form its conjugate base. The first step of this mechanism is the protonation of acetic anhydride with phosphoric acid. So this is very important. So protonation of acetic anhydride with phosphoric acid, this is the first step. In the second step, so let us consider the second step, that is the cleavage of carbon oxygen bond. Cleavage of carbon oxygen bond. Cleavage of carbon oxygen bond to form cleavage of carbon oxygen bond to form acetic acid and acylium ion. Acylium ion to form acylium ion. So if you consider the mechanism, that is double bond O, O, double bond OH having positive charge is there. This is your CH3. Okay, and if you consider in this case there is a resonance, that is the lone pair of this oxygen is goes here, and this bond will shift here, and this bond will shift here. So what do you get here? So if you consider what do you get here? Here a triple bond O, lone pair having positive charge, then this is your acylium ion, and plus what you get here, there is a double bond O here, OH having lone pair, and this is your CH3, that is CH3 C double bond OH. So this is the second step of your mechanism, that is cleavage of this carbon oxygen bond and to form acetic acid and acylium ion. So this is your acylium ion. This is your acylium ion. So this is the second step. In first step, that is the protonation of acetic anhydride with phosphoric acid, and in second step the cleavage of carbon oxygen bond to form acetic acid and acylium ion. So let us discuss this acylium ion undergo resonance. this acylium ion, it will shows resonance, that is O having positive charge. So it will shows a resonance, and what you get here, the carbon having positive charge, and there is a double bond O having lone pair oxygen. So this is your acylium acylium cation. Acylium cation, it will shows a resonance. So this is the second step. So in first step, that is protonation of acetic anhydride in presence of phosphoric acid, and in second step the cleavage of carbon oxygen bond to form acetic acid and acylium ion, and this acylium ion, it will shows resonance. And the third important step, that is the electrophilic attack of this acylium ion on the ferrocene, that is the third step of this mechanism, that is aromatic pi electron attack on aromatic pi electron attack on acylium ion, aromatic pi electron attack on acylium ion. So if you consider this is your Fe, so the hepticity is 5. So in case we shows for mechanism, we will consider this is as, so we know that in ferrocene all carbons are attached to this Fe. For mechanism purpose, we show ferrocene like this, and this it will attack on this C double bond O CH3 cation. So it will attack, the pi electrons attack on this acylium ion. So what do you get here? Fe. Okay, here C double bond O CH3, one hydrogen is there. Here also one hydrogen is there. So C double bond CH3, and this carbon having a positive charge. And what happen in next step, the conjugate base of phosphoric acid, that is O minus P double bond O OH OH, it will takes this proton, and due to the abstraction of proton, the aromaticity of the ring is maintained. The aromaticity of the ring is maintained. That is, so if you consider once again here, that is this carbon having positive charge, so one hydrogen here, C double bond O CH3. This is your Fe attached to this ferrocene. So this conjugate base of this phosphoric acid, it will abstract this proton, and this will shift here to maintain the aromaticity. So what do you get here? So we get our product, that is C double bond O CH3. So this is the mechanism for this reaction, that is acetylferrocene formation with the help of acetic anhydride in presence of phosphoric acid. So you should remember this mechanism. So let us discuss the procedure of this experiment. Let us discuss the procedure. So what are the different steps of these reactions, or the procedure of these reactions, or formation of acetylferrocene, formation of acetylferrocene. So procedure of a reaction, procedure of a reaction. So let us discuss the procedure. So we know that you should remember that whenever you use this phosphoric acid and acetic anhydride, they are irritant, they irritate our body, and therefore you avoid the breathing and their contact with your skin. So you should remember, that is the phosphoric acid and acetic anhydride. Actually, this acetic anhydride is banned, so it is no longer used in chemistry. But for the mechanism purpose, uh, for mono substituted product, we used this mechanism. Actually, in practice, actually in regular practical, we use acid chloride and Levy's acid, AlCl3 and CH3C double bond Cl. But in this mechanism, we will discuss this phosphoric acid and acetic anhydride. So you should remember the phosphoric acid and the acetic anhydride, that is C double bond O, C double bond O, CH3. So both are irritant. So you should avoid the breathing of these chemicals and avoid the contact with skin. And this acetylferrocene, that is the product which is obtained, acetylferrocene, it is also harmful to our body. It is also harmful to our body. Therefore, you should handle this product after its formation very carefully. So let us discuss the procedure. So the procedure is very simple. So you have to take a round bottle flask. So first take a round bottom flask in which you have to take 1 gram of ferrocene. You have to take 1 gram of ferrocene. Then you have to add 3.3 ml acetic anhydride. Acetic anhydride. So you have to take the round bottle flask. Then you have to take 1 gram ferrocene. Then you have to add 3.3 ml acetic anhydride. And then after you have to add carefully 1 ml 85% phosphoric acid H3PO4. 1 ml 85% phosphoric acid. So you heat the reaction mixture in water bath. So to heat the reaction mixture in water bath for 20 minutes with continuous stirring. So to heat in water bath for 20 minutes with constant stirring, with continuous stirring. So the procedure is very simple. You have to take the round bottle flask, ferrocene, 1 gram ferrocene, 3.3 ml acetic anhydride and 1 ml 85% phosphoric acid, and heat in water bath. Heat the mixture in water bath for 20 minutes. And after 20 minutes, pour this reaction mixture into crushed ice. So after heating 20 minutes, pour means add, pour the reaction mixture, pour the reaction mixture into crushed ice, into crushed ice. Pour the reaction mixture into crushed ice. And then after all ice, after all ice get melt, after all ice get melt, you have to neutralize the solution with sodium carbonate. You have to neutralize the reaction mixture with sodium carbonate and cool for 5 minutes. Cool for 5 minutes. So this is the procedure. You have to take first the ferrocene 1 gram, then you have to add acetic acid, acetic anhydride 3.3 ml, then you have to add 85% 1 ml phosphoric acid and heat the reaction mixture in water bath for 20 minutes, and then after heating, pour the reaction mixture into the crushed ice, and then all ice it melt. After melting of all ice, you have to neutralize the reaction mixture with sodium carbonate and cool for 5 minutes, and then you get a product, that is the brown color solid product is obtained. The brown color, so in this reaction, brown color solid product is obtained, and the product, that is brown color solid product, is a combination of acetylferrocene acetylferrocene and unreacted ferrocene. So the ferrocene which is reacted to form acetylferrocene and unreacted ferrocene. So it is a mixture, it is not a pure product, it is a mixture of reactant as well as the product, that is it contains acetylferrocene as well as some unreacted ferrocene. So you should purify this acetylferrocene, you should purify this acetylferrocene with the help of column chromatography. So purify you should purify this acetylferrocene which is formed by column chromatography. So this is regarding to the procedure of formation of acetylferrocene from ferrocene with the help of acetic anhydride and phosphoric acid. So after formation you have to take its melting point, that is melting point of reactant, melting point of product, and you have to characterize both your reactant and product with the help of H1 NMR spectroscopy. Again, if we see the characterization with H1 NMR spectroscopy, then if you consider your ferrocene, in ferrocene all protons of these cyclopentadiene rings are equivalent, and therefore it will shows only one signal in NMR spectroscopy. It will shows only one signal, that is all protons are equivalent protons. So if you consider total 10 protons is there, so 1 2 3 4 5, so all these protons are equivalent proton and they shows only one signal in H1 NMR spectroscopy. But if you consider the product which is obtained in this reaction, that is acetylferrocene, the product, that is C double bond O CH3, this is your Fe. So if you characterize this acetylferrocene with the help of H1 NMR spectroscopy, acetylferrocene with H1 NMR spectroscopy, then in that case, so in this complex we get total 4 signal. So how we get total 4 signal? Then if you consider this complex, it is also a symmetric complex. Then for understanding the signal, so if you draw the structure like this, so let us consider this is your Fe. So let us consider Fe. So we can write this as so let us consider this is your ferrocene, and here your C double bond O CH3 substituent is there. And if you consider the different types of proton, so in this case if you consider here, this is your A type of proton. So this proton attached to this carbon and these carbons are chemically equivalent. So this is your A type of proton. If you consider the proton which is attached to this carbon, it is a other type of proton. It is not same as to this A type of proton, because the environment of this proton is different, because these two protons are in the same distance from this acetyl group, but this B type of proton having a different distance from this acetyl group. And again if you consider this proton, that is the carbon the protons which is attached to this carbon, all these 5 protons are equivalent proton, and therefore they are all C kind of proton. C kind of protons. These are all C kind of protons. So total, if you consider total, the 9 proton of this cyclopentadiene gives 3 signal. It has 3 set of protons. So these 2 protons having A type of proton, this proton. So if you consider here hydrogen, then it is another type of proton, and the remaining protons of these rings are equivalent. Therefore, it will shows 1 signal. So total 3 signals, and this hydrogen which is attached to this methyl group, it will shows another signal in H1 NMR spectroscopy. So it is a D type of proton. So total 4 types of protons are present into this acetylferrocene, because the protons, let us consider, if you consider this is carbon number 1, and this is also a carbon number 1, this is carbon number 2, again here the carbon number 1, carbon number 2, carbon number 3. So if you consider these 2 proton having same environment, therefore they will shows 1 signal. This proton having different environment, it will shows 1 signal. These all protons are equivalent, this shows 1 signal, and this proton which is attached to the methyl group, it will shows 1 signal. So in product we get total 4 signal. In reactant we get only 1 signal in H1 NMR spectroscopy, but in product we get 4 signal. And if you consider again, if you draw the structure, if you draw the structure, then here C double bond O CH3. So this is your A type of proton, this is your A type of proton, this is your B type of proton, and they are of your C type of proton, and the last one is your D type of proton. So A type of proton, it will shows delta value 4.77 ppm. Then B type of proton, it will shows 4.50. Then C type of proton, it will shows 4.20, and D type of proton, it will shows 2.39 ppm. So why this A type of proton shows maximum delta value? Because they are very much close to this electron withdrawing group, that is acyl group, and therefore they are get deshielded, and they shows high delta value in H1 NMR spectroscopy as compared to other type of protons. So this is regarding to the formation, that is synthesis of acetylferrocene and its characterization with the help of acetylferrocene. In next lecture we will discuss the another practicals, its preparation, its mechanism, and its determination. Either you have to find out the percentage or the characterization with help of different spectroscopic technique. Thank you.